Hi everyone. First of all, I would like to welcome all of you in this week's seminar by SML Journal Club. Today, I would like to present my research towards reliable hybrid human machine classifiers that I've been working on since the beginning of my PhD under the supervision of Professor Pavel Casati and Professor Andrea Passarini. By saying hybrid classification, we mean classification problems solved via the combined contribution of humans and machines. When the machine learning model is adopted in the enterprise, as well as in domains from medical to automotive, the machine attempts an inference and a decision on whether to accept the inference or ask a human based on the prediction confidence. The reason is that the machine classification is not always reliable. Let's consider the company Tesla, which made great progress in the field of self-driving cars. Its autopilot technology has made major breakthroughs in recent years, but according to the New York Post last year, there have been 11 crashes in which Tesla was on autopilot or on traffic-aware cruise control have hit the emergency vehicles. So the question remains whether deep learning in its current state will be enough to overcome all the challenges of self-driving. Object detection, velocity, and range estimation plays a big part in driving, of course, but human vision also performs many other complex functions, which scientists call the dark matter of vision. Deep learning models also struggle with making causal inference, which can be a huge barrier when the models face new situations they haven't seen before. So while Tesla has managed to create very huge and diverse data sets, open roads are also very complex environments where new and unpredicted things can happen all the time. This motivates the need for humans in making critical decisions in AI. As I just mentioned, many machine learning models, from classification to similarity, doesn't just return an inference. They also return a measure of how confident the model is, or how likely the inference is likely to be correct. Most research focuses on the return prediction, and so do most metrics, from precision to recall to F1. But that other confidence number is really important for us. It tells us if we should trust the prediction or not. And if not, we probably ask a human or perform some safety fault action. For example, here we see a cat image classified by a pre-trained machine learning model. The inference made by the model is cat, but its confidence is 75% only, which is not trustable if we have a really critical task, especially if the pre-trained confidence threshold is bigger than the machine confidence. Predefined confidence threshold is bigger than the machine confidence. In this specific example, we can say that although the machine is accurate, its inference is not reliable and needs to be verified. This figure shows the typical way in which AI solutions are deployed in an end-to-end enterprise workflow. First, we either reuse or fine-tune a pre-trained model, or use it in a combination with some task-specific model. Either way, we have some ML classifier that, given an input, outputs the predicted class and a confidence, or a distribution of predicted class with confidences. Almost invariably today, in any model deployment, there is then a filtering based on whether the confidence is greater than some threshold. And if so, the prediction is applied, else a default path is followed. Most often, the very same path that was there before the introduction of AI in this process. This is true from autonomous driving or reading X-rays to detecting intents in a chatbot into any use case we can imagine. The point we are making here is that this is not the exception. This is the rule. Almost always, this is how ML is used in practice in any production scenario. And this notion of having some human in the loop in the prediction cycle is not the exception. So if we accept this notion that models are almost always implemented as selective classifiers or selective models, then the way in which we choose one model or the other one changes. Because what we see is that, first of all, the use case derives the value. So given the use case, we have a certain cost for rejecting a prediction, we have a certain cost for applying correct prediction, and we have a certain cost for applying wrong prediction. So use case derives the value of ML models. These value parameters helps us to decide where we set our threshold to accept or reject the model prediction. And because we have a threshold, now what we find out is that the accuracy-based metrics are not the priority for us. If we have a well-calibrated model with arbitrarily bad accuracy, we can still get value from it. The better we are able to identify a subset of items for which our model is calibrated, the lower is the cost for our deployment in our model. And it tells us when it doesn't know. So at this point, I would like to remind you a quote from Socrates, who said, "The only true wisdom is in knowing that you know nothing." And this idea is also valid in hybrid intelligence. In hybrid classification, where the cost of one type of error is really high, knowing if we can trust the ML services is the key for us. As a consequence, the ability to estimate what humans and machines can do and which kind of items they can or cannot classify accurately becomes central to the effectiveness of this service. Considering all of these concepts and the observations we highlight, the problem we are focusing is how to design and implement reliable hybrid human-machine classification services. Now I would like to explain how we envision a hybrid classification service. This figure is taken from our paper in reference to here, which is published by IEEE last year. So here you see that a crowdsourcing platform provides basic access to users and manages the payment. While in most cases, this platform is also responsible for serving the specific items to label. Here we need to take control and override that logic because we need to build a hybrid classification service that we want to be able to decide for which items we need to ask crowd label for and to how many persons. We also want to dynamically stop asking if the combination of machine prediction and the votes obtained so far gives us enough confidence to make a decision. Therefore, the items are loaded externally to the crowdsourcing platform into an item pool. And here you see on the right of the figure. So processing proceeds in batch. And the optimal batch of items can be selected via an active learning strategy or an active learning component, which is peculiar in this case because we have two sometimes conflicting optimization objectives that are asking votes with the goal to classify items in the pool versus asking votes based on what is best for training an ML model that then can help us. This is somewhat more nuanced than traditional active learning approaches, and my colleagues discussed this in more detail in reference 3. So, in order to build such a service, we have many research questions that need to be considered. And actually, we had 6 research questions that we focused so far. And I would like to present you first these research questions, and then we will particularly focus on one research question and the solution we developed. So our first question was related to the active learning component. But before going to explain this research question, let me summarize what active learning is so that maybe some of you didn't heard about it before. So machine learning approaches are challenged both by the lack of training data and by the intrinsic difficulty of the problem. Since obtaining the sufficient training data is hard, active learning emerged as a way to decrease the required size of training data. So active learning is a query strategy to train and obtain a good classifier as fast as possible. Given a set of unlabeled items and a machine classifier, active learning aims at defining a query strategy to progressively sample the most informative items from the unlabeled pool and then obtain the true labels via a human annotator. Labeled instances are then used to retrain the machine learning model. And the main goal is to allow machines be trained with a smaller size of training dataset without sacrificing the accuracy. So let's focus on our first research question. In order to effectively use active learning in such a service, we wondered how we can use the existing active learning strategies in hybrid classification contexts. So are the existing strategies cost-effective, or do we need novel cost-aware active learning methods for hybrid classification services? Actually, for this, we proposed a novel cost-aware active learning technique, and it is published in the Journal of Artificial Intelligence Review last year. So if you are curious about this domain, please have a look at our paper. So the second research question is related to the machine learning classification service, where we think, how does the model calibration affect the performance of machine learning models in hybrid classification contexts? And how can we obtain well-calibrated hybrid classifiers? We also published another paper about these research questions, and I will be explaining more about this research question later in this presentation. So let me skip for now. The third question is how to effectively characterize machine learning failures. So when we think of machine learning failures, we can characterize it as known unknowns and unknown unknowns. Known unknowns are the ones that machine has low confidence, and we already have a signal that the machine doesn't know about these particular items. On the other hand, unknown unknowns are the ones that machine has high confidence, but the prediction is indeed wrong. So we can also refer to this case as high confidence errors, and we know that especially deep learning models are generally suffer from this. So last year, during my internship at TU Delft, we participated to the Cats for ML challenge organized by Google, where we discovered and submitted the adverse images, which are called as AI blind spots or the unknown unknowns for the machines. We were given a part of open images dataset, and we discovered blind spot examples guided by a list of pre-selected target labels. AI blind spots are not the typical adversarial examples defined in the ML literature. Actually, they are manipulated or unreal images which humans can reliably agree on a label, but most of the AI models would disagree. So AI blind spots are the unknown unknowns, or images with visual patterns that cannot be easily distinguished by AI models. So related to this research, we also submitted a paper, but it's still under review. So I hope It will be published soon, and I will be sharing more about this thread with you. If you are interested, please keep an eye on this publication. Research question 4 is again related to this ML classification service. And we wonder what are the proper metrics for the cost of using ML with rejection. So for the problem on finding the right metric to assess the performance of hybrid models, we propose a novel ways to rethink and recompute the real value of ML models. If you are interested, I will refer you to our paper for more details. Fifth question is how to build the rejector. So a smart rejector can be built based on human feedback on machine failures. This can be done in a data-driven way, like the normal ML models are trained, or through hybrid data and knowledge-driven method that allows for more explicit control over the items on which the prediction should be rejected. Reliability of human feedback should be considered as to how human labeled data has been used for ML training. So this thread of work is still in progress, and it's more to become. And the last question is that it's related to how we aggregate ML and human modes, and how to efficiently we can combine crowdsourcing with machine intelligence. And for this research question, actually, you can read more about our approach to combine humans and machines for solving the task of document screening in our NeurIPS paper published in 2020. So here is a summary of research questions I presented. In the remaining part of my talk, I will mostly focus on the research question 2 due to time limits, and I will give references to our papers about other research questions. Let's jump into our main focus today, which is about the centrality of calibration in hybrid classification. Let's remember the architecture of our hybrid classification service. Our goal is to take a step in the direction of developing a science for services that automatically or semi-automatically combine the machine, crowd, and experts in a cost-efficient and effective way to solve batch or online classification problems. The ability to estimate what crowd and ML can do and which kind of items they can classify is the key. So this highlights the centrality of model calibration in the design of such a system. So we calibrate our model when the probability estimate of a data point belonging to a class is very important. In calibration, we try to improve our model such that the distribution and behavior of the probability predicted is similar to the distribution and behavior of probability observed in the training data. Suppose we have a small sample of data points and we want to train a binary classifier. Say we have 10 samples, 10 points, and out of these 10 points, 7 of them belongs to positive class and 3 belongs to the negative class. Then fraction of positive points becomes 0.7. And this is our observed probability. This means that there is 70% probability that a point in this sample will get a class label as positive. Now, we will take the average of probability estimates, which is the predicted probability predicted by the model. And we expect this average to be around 70%. So if this value is far from 0.7, then our model is not calibrated. This figure shows the ideal case when the model is perfectly calibrated. However, we don't get this plot in practice most of the time. At this point, you may be convinced that you want your model to be calibrated. So the question then becomes, how can you achieve calibration? The natural first step is checking whether you have already achieved the calibration in your model. Practically speaking, we are interested in whether your model is calibrated enough. And we can check this by plotting the predicted probability against the empirical probability for some quantile buckets of your data. So miscalibration will be recognizable as a deviation from the diagonal line here, which represents the perfect calibration. Usually, an eye test suffices to diagnose problems, although you could check more formally with hypothesis testing or thresholding calibration-specific metrics. A widely used metric to measure the calibration errors for a multi-class classification model is expected calibration error, which is known as ECE. Here I put a formula, but I know that for most of us, it's really hard to understand at the first glance what we are really computing in the formula. So I would like to show you a running example. And here again, we have 10 samples. And here you see the item IDs, let's say. And we have 4 classes, let's say. Here we see the output probabilities for class 0, class 1, class 2, and class 3. And as you know, in order to get the prediction, we are checking the class with the highest probability for every sample. So what we do is that we identify these highest probabilities for every sample and note it here in this column as the largest probability. And then we also note what is the predicted class for every sample. For example, for the first sample, we see that the highest probability belongs to class 1. So the predicted class is 1. And it's same for the other samples. And in this column, we put the target labels, which means the ground truth labels of each sample. And then what we do is that, of course, in order to understand whether the prediction is correct or wrong, we look at the predicted and target class. So if they are the same, this means the result is correct. Otherwise, it's wrong. After this point, what we do is that we try to divide the 0-1 probability range into a fixed bin size. For example, here we pick the number of bins as 3, but this number of bins can be changed based on the use case, based on the model, etc. It's another research question. So here, let's say that our bin size is 3, number of bins is 3. So it means that we divide 0-1 range into equal size of 3 bins, which means that, for example, in the first bin, we take the probability range from 0 to 0.33, and same for the other ranges. And then what we do is that we count the number of samples belong to each bin. For example, for the first bin, we are looking at how many samples we have that the highest probability, largest probability belongs to this range. And we can see that we have 0.28 and 0.31, and that's all. So we have 2 samples in this bin. And we compute this for each bin. Then we find the accuracy. For example, for this case, the first sample is correct, the prediction is correct, and the second one is wrong. So our accuracy is 0.5. We compute these accuracy values for every bin. Then we also compute the average probabilities in this bin. So for example, for this one, we take the average values of 0.28 and 0.31, which corresponds to the 295. After this step, what we do is that we take the difference between the accuracy and the average probability scores and then multiply by the number of samples in this bin. We do this for every bin, sum these scores, and divide them by the total number of samples, which is 10. And this value gives us the expected calibration error of our model. So let me talk a little about the related works about this calibration stuff. So if you discover that your classifier is miscalibrated, you might want to start fixing the classifier itself. A well-known technique is flat scaling or temperature scaling. A very common technique in the literature for model calibration is label smoothing, where hard class labels used in the cross-entropy laws are smoothed into a probability distribution across classes. However, probability amortization in output targets can bring extra noises, and prior art really didn't provide insights in how to set label smoothing hyperparameters. An alternative approach is known as soft targets, where we create an empirical distribution over crowd loads. While the existing work has found that model performance is sensitive to noise in soft targets, none has investigated the effect of label fusion methods on model training. Label fusion methods are widely used in crowdsourcing to aggregate human answers into one label, for example, David Skin or GLAD. So far, we discovered the details of our end goal hybrid classification service, and we discussed that the calibration is the key component for such a service. In the rest of this presentation, I will be presenting our study on the effect of label smoothing and soft targets on model calibration in NLP tasks when training labels are crowdsourced. And this is quite old work, like we did it in 2020 and it is published last year. And the typical approach to deal with crowdsourced data is to aggregate votes for each item into a gold label, often using majority voting or expectation maximization methods. We proposed alternative soft target approaches in this work. So let's examine our proposed soft target approaches. In the first approach, namely the soft, we define a function f that takes crowd labels as input and outputs a set of workers' accuracies and a probability assignment via a label fusion technique over the classes for every sample. In the second approach, namely the soft hard, we perform one-side smoothing that we identify the probability of most likely label via a label fusion method and assign 0 probability to all other classes. So what I'm talking about, maybe you are not familiar with label smoothing, soft target, and all. So let me show you a figure that will make this idea more clear. What I mean by hard target is that, for example, in the prediction, we assign probability score of 1 to the predicted class and 0 to all other classes. Suppose that here we have three class classification. And if we are using the hard target approach, we only give the probability 1 to the predicted class and the others is 0. So if we use label smoothing, this means that we are smoothing the probability of the predicted class by a parameter alpha. For example, if it is 0.2, this means that we assign the probability of 0.8 to the predicted class, and then we divide the remaining probability value across different classes. So the rest of the classes takes the equal probability, and the sum should be 1. So in the soft target approach, we again smooth this predicted class probability, but then the rest of the class may get different probabilities. It doesn't have to have the same probability. And in the semi-hard target approach, what we do is that we don't want to take the noise of the unpredicted classes in the prediction. So what we do is that we just smooth the probability of the most likely class and then assign 0 probability to the other classes. So we don't care about this. If they have any noise, we don't want to carry that on the prediction. So in our experimental setup, we used 13 crowdsourced datasets in total, 3 of which includes the individual crowd plots, while the 10 of them only have the aggregated plots. We evaluated a simple one-layer neural network and a fine-tuned Distilbert model. We trained them with the cross-entropy loss using hard targets, label smoothing, and the proposed soft target methods. We tested the impact of 3 label fusion methods: majority voting, David-Skin, which decides based on the worker reliability, and GLAD, which further considers the task difficulty. Here you see the performance of models with targets obtained from different fusion methods. We accept the hard targets as baseline and analyze how label smoothing technique and our proposed soft target approach improve the baseline. Results show that our soft target approach improves ECE across all datasets up to 15.7%. Here you see a figure which shows the confidence histogram of the Distilbert model when we use hard targets and when we use soft targets. As you can see, if you use the hard targets, we see a right-skewed shape of these number of samples across the probability of 1. So it means that it's overconfident. And in the case of soft target, we can see that these probability distributions are more diverse. And here in the second row, we see the reliability diagram for the same cases. So in this one, we see the reliability diagram of this Distilbert model with hard targets and here with soft targets. As I mentioned before, this red line here in the diagonal shows the case of perfect calibration. And the output, model output is shown with the blue and the gaps are shown with red, which means that here we have many misclassification cases. And in this case with soft, we can see that it is really improved. So the ECE is lower in this case. When we look at the performance with our second proposed approach, we see that soft hard targets improves ECE on 2 datasets while it remains comparable in 1 dataset. Here you see the average improvement of soft targets and label smoothing compared to hard targets. Results show that our proposed soft and soft hard target methods substantially improves the model calibration. So our takeaway messages are as follows. Calibration is central in contexts where the loss function is skewed and the cost of error is high compared to the cost of asking humans. Second takeaway is soft and soft hard targets help improving the calibration of text classification with crowdsourced data. And the last one is that the effect on calibration error and the benefits of the proposed approach are manifest for deep models that are known to be more affected by calibration issues. Here I put some references. Thank you so much for your attention. If you have any questions or comments, you can reach me via these emails.